All right, today's class is about a problem called 2SAT. So it's building on what we did last time, which seems like a really long time ago. So let me remind you and remind me what we did. So 2 Thursdays ago, nope, 2 Wednesdays ago, we introduced this SAT problem, which was just Boolean logic, and, ors, nots. We defined a couple different versions of this problem. Maybe the starting one was just a general Boolean formula, which can have lots of nested parentheses and stuff like that. And, the basic question was, can we find, given a formula over some Boolean variables x1 through xn, is there or can we find some way to set x1 and x2 and x3 to be either true or false so that the whole formula comes out to be true? It's a satisfiability question. And simple question, and it doesn't really look like that hard of a question, hard of a problem initially. I feel like it doesn't feel like as interesting as some of the graph problems we did. It seems like Boolean logic should be kind of straightforward. But nonetheless, we don't have a polynomial time algorithm. And that's the big question, is there a polynomial time algorithm? And so we start looking at restricted versions of the question, such as when the Boolean formulas are in what's called conjunctive normal form. So that means like it should be an and of ors. Okay, so it's relatively flat if you drew out the tree. So very simple structure. Is this version of the problem maybe easier to obtain polynomial time algorithm? But the answer was no. We were able to show that you can take any general Boolean formula and turn it into CNF form while maintaining satisfiability. The main trick there was this assignment gadget, where we kind of take subtrees of the formula, so to speak, and introduce a new variable equal to the output of the subtree. And this way we can kind of gradually take that deep tree and turn it into a flat thing. Okay. We went even further and we looked at 3SAT. So this is like CNF, but now you only have 3 variables in every clause. X1 or X2 or not X3 or something like that. That seems to be awfully simple. Can we do that? And the answer was no. In fact, that satisfiability gadget naturally produces pretty small clauses. So you can't do 3SAT either unless you could do Boolean SAT. General Boolean formulas, which seem pretty tough to begin with. Last one we looked at was circuits. This is more general than Boolean formulas because now means anything that's described by a logical circuit and trying to get some inputs that make the circuit output true. But again, we realized that any circuit can be turned into a Boolean formula, actually using the same equality assignment gadget, if I remember correctly. So all these problems turned out to actually be, we don't have polynomial time algorithms for them. It'd be great to come up with one. People do think about this problem. But we did establish that if you get a polynomial time algorithm for one, you get a polynomial time algorithm for all. So we didn't solve the initial question, but we did learn something about the problem and also maybe have some explanation for why we're frustrated even on the simpler looking ones like 3SAT. Okay, so that's where we left off. So we're going to push even further in the direction of 3SAT, past 3SAT, and look at the 2SAT problem. Okay, so 2SAT, it's like 3SAT, but now we have 2 variables for every clause. Okay, so so there's a 2SAT formula up there, x1 or x2 that has 2 variables in it, not x1 or x2 that has 2 variables in it, so forth. So we asked the same question: can we come up with a polynomial time algorithm for this problem? Okay. Besides 2SAT, we're going to look at another closely related problem. It's called max 2SAT. Okay. So up to this point, we're always given a formula, and I want to make the whole formula output to be true. Okay. This one's going to be a little bit different. You're given a formula just like 2SAT. So it's going to be conjunctive normal form, and there's going to be 2 variables in every clause. But rather than trying to decide if the entire formula can be satisfied or not, we're just going to try to satisfy as many of those clauses as possible. Okay, so it's called max 2SAT. The goal is to try to find an assignment that satisfies as many of the clauses as possible, or alternatively, figure out what that maximum number is. Okay. So that's the max two-sat problem. Similar, a little different. Okay. Any questions about these problems? All right. To get everyone excited, I set up a poll. Okay. So we're going to vote whether for each problem there's going to be a polynomial, where we expect there to be a polynomial time algorithm, or if we'll find out maybe it's just as tough as some of those problems from last class. Or we won't vote. Okay, those are your three options. Okay. Let's do two-sat first. Who's not voting? Okay, two of you. Okay. Who thinks we'll be able to come up with a polynomial time algorithm this time? Okay, I'd say like 66%. And then who thinks it's going to turn out to be hard? Oh, wow, okay. Didn't do something right. All right, fine. Doesn't have to add up to 100%. Okay. All right, so that's the vote for two-sat. All right, max two-sat. Who's not voting? More people. Okay. As the lecture goes on, within 10 seconds, you're already over it. Okay, excellent. All right, who thinks that there will be a polynomial time algorithm for max two-sat? Looks like maybe a little bit less. And who thinks it'll turn out to be hard? That also looks like a little less. Okay, clearly not an exact system. Okay. Now, first of all, if we just compare them to each other, uh, if I can solve two-sat, does that mean I can solve max two-sat? Yes, why? So if I give you an instance of max two-sat, how would you use two-sat to solve it? So two-sat would tell you if all the clauses can be satisfied or not. But for max two-sat, I'm not really interested in just the all or nothing question. I'm interested in, can 50 of them be satisfied? Can 100, can 99% of them be satisfied? So two-sat doesn't solve max two-sat. On the other hand, if you could solve max two-sat, can you solve two-sat? Yeah, because you can plug it into your max two-sat and find out if all 100% can be satisfied. So there's no way that max two-sat is going to turn out to be easier, in the sense that the one thing we can rule out is that max two-sat has a polynomial time algorithm and two-sat doesn't. That's one case that we can rule out. Other things are all in play. They can both be hard. They can both be easy. One could be easy. One could be hard. All right. Okay. All right. So we're going to start off with two-sat. All right. If you guys still remember, those of you who voted that it was going to be hard, any ideas or instincts, or why did you think it might be hard? It could be fine to say, it kind of looks like last week's class or 2 weeks ago's classes. Any idea is fine. But what compelled you to vote that it might be hard? Maybe compel is too strong a word, but yeah. Okay, just not that different from three-sat, going from 3 to 2. Was that most people's reasoning? Okay. And what about why did some people have hope that it might turn out easier this time? Certainly. Yeah. No, yeah. So at least going from 3 to 2 shouldn't make it harder. I mean, it seems like there's less degrees of freedom. So it's 2 small enough where maybe something clicks and somehow we can do something. Is there a difference between 2 and 3? Is sort of the question. All right. So suppose I was trying to make an algorithm for a two-sat. So here I give 2 different formulas. One of these is satisfiable and the other one isn't. Which one is satisfiable and which one isn't? The first one is what? The first one is satisfiable. Some people disagree. Why is it unsatisfiable? Or it's satisfiable, you should be able to give me some assignment that satisfies it. There's only two variables. And if it's unsatisfiable, maybe you can somehow compactly try to describe why not. Yeah. Yeah, so we actually had this example a couple weeks ago, but this is enumerating all the possible ways to combine x1 and x2. So even if you had set both of them to be true, then the x1 false, negative x1, negative x2 would come out false. Yeah. Sorry, you can compress? You're saying right here there's already contradiction? Oh, okay. So yeah, at some level you can replace this with x2 because the x1 is not going to help for one of the two. Yeah, that's true. Okay. Okay, so this one is unsatisfiable. And what about this one, the second one? 0, 1, 0, 1, 0, 1, 1, 1, 1, 0. So we get a 1 in each one. Okay, so it is satisfiable. I think all I did was I deleted this clause, the third clause from the top one. Okay, so some more satisfiable. All right. Any ideas? Because, okay, so there will be an algorithm. We are now going to try to come up with an algorithm for 2SAT. And the key ideas are coming up on the next slide. Once I show them to you, you'll never get to guess again. Any crazy ideas as to how to come up with an algorithm for 2SAT? Yeah. Okay, how might I make a graph? Okay, well, it's not that crazy of an idea because it's awfully close to what's coming up. Okay, so there's this sort of with 2SAT with two variables per clause. There's some kind of forcing going on, right? If we just look at like the first clause here, x1 or x2. If I set x1 to be false, then I know I have to set x2 to be true in order to satisfy that clause. If I set x2 to be true, then I have to set x1 to be false. So there's sort of like these implications, where some assignments force further assignments. And whenever you have a binary thing like that, okay, maybe there's some chance that we can model it as a graph, right? Edges also have two endpoints, and see if we can look at the graph and do some stuff. So that's exactly what we're going to do. What did I have in mind here? Something? Oh, okay. All right, okay, yeah, okay. All right, so let's walk through this example, and this will go through this binary thing. Okay, so for example, suppose I speculated that I'm going to set x1 to be true. Okay. Then if I look at this second clause, then the second clause says I have to set x2 to be true. Okay. On the other hand, if I look at the last clause, it tells me that x2 has to be false. All right, and here I sort of find some kind of contradiction. But one thing nice is like, okay, I tried guessing one thing, and then everything becomes forced, and I can kind of chase it through. If it was 3SAT, there would be like another branching, right? There would be kind of two options if there's three variables there. But for two variables, once I choose one, then it might force me to do something on another. And we can do something if I had tried setting x1 to be false. If I set x1 to be false, then I look at that first clause and x2 has to be true. Right? So if I look at this first clause here, as soon as I set x1 to be false, I know x2 has to be true to make this satisfying assignment. On the other hand, if I look at the third clause, x1 or not x2, that tells me x2 has to be false. So I'm forcing two things that contradict each other. So this kind of forcing game is at least viable with 2SAT and not so straightforward with 3SAT. Because if you took away one thing, you still have two kind of degrees of freedom left with 2SAT. But here it's much more forced. All right, so the graph that was described, a not so crazy idea when I had strictly asked for crazy ideas, will be as follows. For every variable xi, I'll make a vertex representing kind of xi, not xi. So I think of the vertex for xi as setting xi to be true. And I think of the vertex for not xi as setting not xi to be true or xi to be false. Okay, so for each of those two literals corresponding to xi, I'll have a vertex. So each variable becomes two vertices. Okay. And for each clause between two literals a and b, so a could be xi or a could be not xi. Okay. I'm going to make an edge from not a to b, because if I set not a to be true, which is to say I set a to be false, then I have to set b to be true. So I'm going to make these edges sort of whenever one endpoint is true implies the other one has to be true is the logic behind these edges. So the other direction is for a or b, I'll have an edge from not b to a. Okay, so that means if b was already not xi or something, not b would be xi. All right, so that's what we'll do. We'll try to visualize our 2SAT formula, and in particular, all these forcing steps in a sort of graph-like structure. All right. Okay. Good. So, all right. So for an example like the one we've looked at several times, here I've set up the four vertices corresponding to the two variables, one of each type. Okay. So if I look at this first clause, like x1 or x2, that'll give me two edges. One edge will go from not x1 to x2. Cool trick. I can make arrows now. Okay. So I can go from not x1 to x2. And then the other direction is if I set x2 to be false, then I have to set x1 to true. So that'll go from not x2 to x1, like that. Okay. And so you would generate edges in this format, and you end up generating 8 edges for these 4 clauses. I won't do it in front of you. I did it ahead of time. It's also cleaner this way. All right, so this would be the implication graph for our unsatisfiable formula. Okay, so it has 8 edges, 2 generated by each clause. All right, so in general, if I set x1 and xn to some values of true or false, so for some assignment of the x's, okay, that will be a satisfying assignment for f if and only if it doesn't violate any of the edges. If and only if I don't have anything of like false to true. So I can have, I never have anything like true to false. I can have false to true, I can have false to false, and I can have true to true. But I'm not allowed to have true to false. Because the edges are, if I set the first point to be true, the opposite endpoint has to be true. Those are the rules for the edges. So if I can come up with an assignment that makes all the edges happy, it'll make the formula happy. Conversely, any assignment that makes the formula happy makes all the edges happy. Right? Okay, so we've sort of transformed it to a graph problem. I've also drawn the implication graph for the satisfying assignment. Again, all I did was drop one of the clauses, so it's just a subgraph where I dropped two of the edges. Okay. So that will be the implication graph for that earlier example that is satisfiable, I think, by By what? Yeah. So so let's do an example. Okay, so we know this is unsatisfiable. So no matter how I set x1 and x2, there should be some issue. So I'm going to set arbitrarily. Actually, it's all symmetric, so it doesn't matter. I'm going to set x1 to be true and x2 to be true. I could do the other one if you wanted me to, but let's just say I did that. That means this one will be false, and this one will be false. Okay, and I said the bad edges are the ones um, that are going from true to false. Okay, so one such edge could be this one. Okay, so here I said x1 to be true, and I said x2 to be false, or x2 bar to be false. The negation of x2 to be false, which means I had set x2 to be true. And the corresponding clause, I don't know if you guys can see, the clause for that edge is here, x1 bar or x2 bar. Okay, and indeed, that is a clause that's being violated by our assignment, right? Because I had said x1 to be true and x2 to be true, which means that that clause, x1 bar and x2 bar, x1 bar or x2 bar would come out false, right? That's the clause we're failing. And that's exactly the edge that's sort of like not happy, where I haven't, the starting point is true and the end point is false. So by true to false, I mean I have some directed edge where the starting point is true and the ending point is false. Our edges were based on like, if this was true, then the other one has to be true. That's how we set them up. Did that answer your question? No, maybe not. So maybe it's helpful to look at the initial construction. So the logic here is that if I have some clause A or B, okay, that means if I set A to be false, then I have to set B to be true, right? So in particular, if I set A bar to be true, which is the same as setting A as false, then I have to set B to be true, right? So true has to go to true, and it cannot go to false. That's the main rule. Same was here. If I set B bar to be true, which is the same as setting B to be false, that clause says that in order to satisfy it, A has to be true. So again, true forces another true. So this is a graph where whenever one vertex, which represents a literal, it could be an xi, it could be an xi bar. Whenever that literal is true, all of the vertices it can reach also have to be true. So we can check here. What was the satisfying assignment for this? 0, 1 or 1, 0 something? 0, 1, okay. All right, so that's false, true, true, false. Okay. And I'm worried about edges that start at true and go to false. That's what I'm worried about. So I just have to check this guy's outgoing edges and this guy's outgoing edges. And okay, this one is okay because true is going to true. And this one is okay because true is going to true. Okay, so this checks out. This satisfies all the happy edges. It also satisfies. It makes all the edges happy. It also makes the formula happy. All right. Okay, so, right. Okay, so, all right, so we know that one of these formulas, the one on the left is unsatisfiable, the one on the right is satisfiable. Is there some way I could have looked at this graph? I could have looked at the graphs and come to this conclusion. There's some issue in particular with the graph on the left that sort of shows you that it can't be satisfied. Yeah. Yeah. So if I can make a cycle where I start at x1, right? And I go this way, and in that way, and in that way, and in that way, right? Now I have to set either x1 to be true or x1 bar to be true, and the other one to be false, right? So if I set the first one to be true, okay, then it's going to say, oh, x2 has to be true. And it says, oh, x1 bar has to be true, but that can't be the case because x1 bar has to be the opposite of x1. And if I had started at x1 bar, oops, and I had set x1 bar to be true, right, which is say I set x1 to be false, then this says, oh, x2 bar has to be true, and x1 has to be true. That can't be the case. x1 and x1 bar have to be opposite. Okay, so we have a directed cycle uh, with both of the literals corresponding to the same variable in our implication graph. So whenever you find one of those directed cycles, you know right away it can't be satisfied. There's some kind of contradiction in the implication graph. That's not the case on the right. Are there any directed cycles? I don't think there even are cycles in the graph on the right, let alone cycles that involve both parts of the same variable. All right, so this is actually what we're going to leverage. This will be the main insight to our thing. Okay, so the claim is, I put everything on the right. The claim is that a two-sat formula is satisfiable if and only if for all variables xi and xi bar are not strongly connected, they can't both reach each other, both directions, in the implication graph. That's the claim. Okay, and we'll actually even come up with an algorithm that will construct a satisfying assignment if they aren't, if this condition doesn't arise. All right, so one direction of the proof is easy. We just did it, right? If two variables, if xi and xi bar are in the same directed cycle, then you have this implication that leads to a contradiction. So, okay, one side is easy, right? So the more interesting direction is to assume that, no opposite pair, no xi and xi bar are strongly connected in the implication graph, and now we want to prove that you can extract a satisfying assignment. Okay. Well, what's here? Okay. All right, maybe I should ask at a high level, any fun ideas? Any first steps? Chase it all the way through? Well, okay, that's an idea. Let's just start with x1, sign it to true, follow it through, sees what happens. Maybe it doesn't work out. Then we try x2, x3. My worry, I don't know how to prove that terminates very quickly. It feels like you're just guessing things. And then you can maybe knock out some, but maybe not all. Yeah. Okay, so there may be some easy cases where if for example some xi can reach xi bar, okay, but not vice versa because they're not strongly connected. Okay, so if xi can reach xi bar, then there's only one possible assignment for xi, which is false. Because if you had set it to be true, then it'll be following along some sequence and eventually tell you that xi bar has to be true, and then that would be bad. Okay, so if you have an obvious case like this, then you can figure out the right assignment for xi. Okay, but what if you don't? So it's true. This doesn't hurt you. Those assignments will be correct. How about an idea? What if I told you the implication graph was a DAG? It's not necessarily the case, but it's just a simple case. What if the implication graph turns out to be a DAG? Well, we want to confirm that it's satisfiable. Well, at the end of the day, we're going to show that if it's any graph, it's for sure satisfiable. So you can't just tell me if it's a DAG, it's for sure satisfiable. You got to give me more reasons than that. Yeah. Okay, let's say we've already topologically sorted it. So you're walking through. What do you do with that? What do you do with the first one, the second one? But that seems not so different than just guessing everything. We're not. I feel like we're not really leveraging. Yeah. Yeah. Oh, so we're already in a case where we already know that no xi and xi bar in the same cycle. So we've already ruled that out, which is an obvious certificate that the formula can't be satisfied. So it is true that X have no cycles. Well, suppose you were going to label. All right, so DAGs have sources and sinks, right? So often you just say, "Oh, what should I do with the source, or what should I do with the sink?" Okay, so let's say that let's say that xi is a source, or the source is some xi. So the rest of the graph is all over there, right? Okay. And if you were, say, to process sources first or sinks first or something like that, you might start and say, "Oh, what should xi be?" False. Okay, why false? Okay, yeah. So if I label this false, it will not create any issues for anyone else down the line. If I did create assign true, now it has tons of ripple effects. It creates a lot of responsibility for all future decisions. But false is safe. Assigning a source to false is never going to cause an issue in terms of violating an edge. Okay, on the other hand, that means I'm going to set xi bar. Xi bar is going to be equal to true, right? Okay. If xi is a source, what do I know about xi bar? Yeah, that's true. Xi bar cannot reach xi, so that's good because that would be an issue right away. But there's something even stronger. If xi is a source, think about how our edges are constructed. Is it always what? Well, if you're going to set xi to be false, then xi bar has to be true. Just because the negation of false is true. Why? Okay, so the way we constructed our graph, every time I made an edge leaving, say if this was xi, right? If ai bar was xi, that means a is xi bar, right? So every time I make an edge that's leaving xi, I'm making an edge that's going into xi bar, and vice versa. So if xi only has edges leaving it, then xi bar has only edges coming in. Okay, so that means xi bar That means xi bar is a sink. Why is that good news? Yeah. So for the same reason that I don't want to set a source to be true, I don't want to set a sink to be false. Because if I had set xi bar equal to false, right, then everything coming in has to be false. It can't be true. Right now I would have to go backwards and propagate falses all the way backwards. But if I had set it to be true, then I'm not creating any obligation, right? I'm not creating any obligation for future choices, right? That's great. So that means I can, set the source to be false. The sink, the corresponding complementary thing is automatically a sink. I set it to be true, right? And then I'll just delete this from the graph. I remove it and all. My goal is just to satisfy all the edges. I'm not even worried about the formula anymore. So I'll just remove those two vertices, which are labeled, and all the edges. And then what? And then what? The next source, the next sink. There will be a new source and a new sink and a new day, right? Because it's still a DAG. So I can go through and process all the sources and sinks. I set the sources to be false, the sinks to be true, and gradually eat away at the whole graph. Okay. All right. So that works for a DAG. What about a general graph? Sure. So it has to do with this sort of the symmetry in how we construct our implication graph. So whenever I have an edge from A bar to B, it's complemented by an edge from B bar to A. So in this case, since xi is a source, I should think of A bar as xi, right? So there's an edge leaving xi. And that means the complementary edge is an edge going into xi bar. So every edge leaving xi corresponds to another edge going into xi bar. And if there was an edge leaving xi bar, then that would be an edge going into xi. But xi is a source, so that can't be the case. So there could be no edges leaving xi bar, and so xi bar must be a sink. Yeah, it has to do with this sort of dual nature of this implication graph, this kind of symmetry, extra symmetry. Okay. All right. So now, okay, that was the case for a DAG where you have sources and sinks. I'm taking the sources and sinks away. I'm giving you a general graph. Yeah. Okay, that's always a good answer. So almost any time, if I ever give you a two-part question where part one is what about a DAG and part two is what about general graphs, a reasonable idea is to see what happens when you take strongly connected components because it takes a general graph and turns it into a DAG. So, okay. So consider some kind of strongly connected component in the implication graph. So here I made a very small one with just 3 literals. Okay. Whatever I set x1 to be, if I set x1 to be true, the next 2 bar has to be true, and the next 3 has to be true, right? And likewise, if I had set x1 to be false, then going in the opposite direction, x3 has to be false, and the next 2 bar has to be false, and the next one is false. So all the literals in a strongly connected component actually always have to be the same assignment. Okay, so that's great. So at some level I can kind of contract. And now one thing sort of important is that dual nature, right? For xi, there was always an xi bar. That was important for our argument before. So is that also going to hold for strongly connected components? Yeah, so, all right, so every A to B has some bar B to bar A, right? So X can reach Y if and only if bar Y can reach bar x or something like that. So for every strongly connected component, there's another strongly connected component where for each variable, I take the negation. X1 becomes x1 bar, x2 bar becomes x2. And I reverse all the edges. Now it's spinning in the opposite direction, I hope. Okay, so it's a complementary strongly connected component. Again, all the variables have to be the same. And between one component and its opposite component, they have to have the opposite assignment. These are all true and these are all false, or these are all false and these are all true. Okay, so lots of nice things are working out. Okay, so how would you now put the algorithm together? You have all the pieces. So I give you a graph. I give you the implication graph. It's not necessarily a DAG. What are the steps you take? Take the strongly connected components. Okay. So now I have this like DAG of strongly connected components, each of which represent a handful of literals. Okay. And what do I do next? We can grab a source component. Yeah, we'll set everything. Actually, I think we set everything to false for the source component. False. And then for the same reason as before, the complementary component is going to be a sinc component. Because any edge leaving the source component corresponds to an edge going into the sinc component. So luckily, that same component will be, the complementary component will be a sinc, and we can set it to be true, I think. Okay. All right, so perfect. Okay, so I did it in terms of peeling sinks and then looking at the source, but that's the same thing. Right? So we'll assign everything in the sinc to be true, everything in the source to be false, right? And then just continue recurse kind of thing. Okay? And then the key idea, which we all know by now, is that as long as I'm assigning sinks to be true and sources to be false, I'm never going to violate an edge. Don't violate any edges. If I don't violate any edges and I label everything, I'll walk away with a satisfying assignment. Okay. So to put it all together and make it fast, I guess here's the code, but it's nothing special. In general, you take F, you build the implication graph. That's not too hard because you just go through and check each clause. That'll take linear time. You compute the strongly connected components. That takes linear time. We did that a few weeks ago. Then we'll check all the components to see if xi and xi bar appear in the same component for any I. If it does, then we can return that component as like proof that F is unsatisfiable. Here's a strongly connected component containing both literals for the same variable xi. I know that F is unsatisfiable. Here's proof. Otherwise, we can process sources first or sinc first. I wrote it as sinc first, but we can just go from sincs on down, set this to be true, set the corresponding thing to be false, and just march all the way through. All right, so how long does that whole algorithm take? Okay, why? Which step takes more than m plus n? Oh, sorry. Let's say that m is the number of clauses. Okay, sorry. I should have at least said that. All right, if m is the number of clauses in the formula, which is roughly the size of the formula, and n is the number of variables, then your whole algorithm takes only m plus n time. Okay, so in fact, not only can you solve 2SAT, but you can solve it like as fast as humanly one could possibly expect. This problem turns out to be very easy in some sense. Okay, Any questions about 2SAT? All right. Next up, it's max 2SAT. So it's like 2SAT, which we just did, except I'm not worried about things being completely satisfiable. I want to satisfy as much as possible. Question, is there a polynomial time algorithm for this? Are we going to get lucky twice? All right. Okay. I set up another vote just to see if anyone changes their mind. Okay, so we know that 2SAT has a polynomial time algorithm, so I won't ask for that vote again. So now let's do max 2SAT. In light of the fact that 2SAT is polynomial time solvable, who's not going to vote? Oh, great, everyone's on board. All right. Who thinks that we can come up with another polynomial time algorithm for max 2SAT? Let's see, it's like 55. Okay, and who thinks that actually it'll turn out to be hard? Okay, I think that's like 35. All right. Okay, so liars have gone up over the course of the class. Okay, great. All right. Okay, so all right, it's going to actually turn out to be. Okay, for polynomial time, what was the intuition? Who thought it was going to be polynomial time, and what was their thinking? It doesn't have to be a great reason, but yeah. Okay, so the first step is to create that graph, right? I can create the implication graph and topologically sort it. One thing I'll point out though, when I look at like x1 or x2, right? The logic was if I set x1 to be false, then x2 has to be true in order to satisfy the whole thing. So we draw these edges like, oh, x1 bar to x2, because if I set x1 to be false, I have to take x2. And if I set x2 to be false, then I have to take, not much of a 2, then I have to take x1. That was the thinking. That's how we designed this graph. Now, that's not exactly the case here. Why? Sorry. Yeah, in particular, we don't have to satisfy every clause. So if I set x1 to be false, I could also set x2 to be false and say, I just give up on this clause. It's not worth the trouble. We're going to satisfy everything else. So the implication is not as set in stone. Right? It's not true that the solution has to make all the edges happy. You do want to make as many edges happy as possible, I think. Maybe you can show that. But you don't have this complete exact forcing thing as before. All right. Anyone who thought it was hard, what was their thinking? Or what was their thought process? Or was it this? Or was it just they thought I would zag? Yeah. Okay. All right. So to summarize, we thought there might be a polynomial time algorithm for max 2SAT because it sort of looks similar and maybe we can do some implication stuff. And then those who thought it would be hard felt that it had bad vibes. All right, that's fair. That's how I feel about many problems. So vibes are important. What else do you have to go by in this world? Okay. All right. So your vibes are correct. We are going to show it's hard. Okay. You just have to fine tune your vibes for the test. So we're going to try to show it's hard and try to reduce from 3SAT to max 2SAT. I think that's kind of surprising given, I think actually polynomial time is maybe the more natural thing to think after to me it looks more like 2SAT than 3SAT, but we'll see what happens. Along the way, instead of going directly from 3SAT to max 2SAT, it's going to be a little bit easier to introduce an intermediary problem called max less than equal to sat, which is saying I'm allowed to have variable clauses one or two variables in it instead of exactly two. And then afterwards, we'll figure out how to go from one or two to exactly two. Okay. All right. So yeah, this also probably has bad vibes. All right. So we're going to show first that a polynomial time algorithm for max, at most two sat implies a polynomial time algorithm for general sat. So when I just write sat, I usually just mean CNF sat. That's what most people mean. But in general, by now, we know all those problems are hard. So, if you had confused it for Boolean sat, it's not the end of the world. Okay. All right. So here's how we're going to try to prove this. Structurally, at a high level, I want to show that a black box for max less than equal to sat. So let's say the black box can take a two sat formula and output what's the maximum number of satisfiable clauses. So just output a number. Okay. And I want to use that black box to figure out if a three sat formula is satisfiable. Okay. So this is a little bit different than the reductions in the past, because before we're reducing like a yes-no problem to a yes-no black box. Here I'm reducing a yes-no problem to a numerical output black box. So we'll have to also kind of do some translation on the way back. Okay, so, all right, so I need to make the input fit the black box. So somehow we're going to take the three sat, try to turn it into some kind of two sat. I'm allowed to generate more variables, more clauses along the way, as long as G, the size of G is like within a polynomial of the size of F. So that polynomial running times stay polynomial running times. And we'll submit that to some black box that can solve the max at most two sat problem. Okay. And then, we'll be told, oh, what is the maximum number of satisfiable clauses? And somehow we'll have to convert that into a yes-no answer for the original question of whether F was satisfiable. Okay, so that's the general circle of life. Okay. All right, so what do we need to do? I need to figure out how to convert a CNF with 3 literals per clause to a CNF with at most 2 literals per clause. So I think in particular, it probably is fine to just look at one clause at a time. Just figure out how to take one clause, with 3 literals A, B, C, and turn it into a bunch of 2 or 1 variable clauses. Okay. All right, again, the answer is coming up on the next slide, so I thought I'd give you guys the chance to guess. Any crazy ideas how to go about this? How can I turn A or B or C into some useful family of 2 variable clauses? Replace B or what do you mean? Like replace both of them, or replace B and then replace C? Well, like when you say B or C, what do you mean? Oh, the combination. Okay, so I introduce some new variable Y. So I have A or Y. Okay, so that's one. Yeah. Okay, A and then B or C. Okay, actually, is this one? Okay, so let's at least work through this. Okay, so the idea is, okay, here's 2 clauses. One has just A, and the other one has B or C. Okay, and so at some level, if A or B or C, if that whole original clause came out to be false, then in my 2 clauses I would get 0 points. And if it came out to be true, I would get at least 1 point. So that's kind of good because it differentiates the gap a little bit, right? If I get A or B or C, I mean the original clause completely false, I get 0 points. And if I had gotten it right, I would get at least 1 point out of the two possible. Okay? The downside, though, is that if that original A or B or C came out to be true, then it could be that either, I mean, I could get 1 or 2 points, right? Maybe A is true and B is true, so I get 2 points. Or maybe just A is true and I get 1 point. That doesn't seem like a big deal with one clause, but if I do this to all the other clauses, let's say there's 2 clauses, I can't differentiate, so I apply this trick to two different clauses. It could be the case that both of the 3 clauses, the groups of 3 were correct, and I got 1 point for each, so I get 2 points total. Or it could be the case that the first group of 3, I got 2 points for it, and the second group of 3 was not satisfied, and I got 0. Either way, I'm getting 2 points, but in one case, both of the clauses, the original clauses, were satisfied. In the other case, only one of them was satisfied. So actually, the only technical issue is that when A or B or C comes out to be true, it could be 1 or 2 points. If I could somehow enforce that it's always 1 point or it's always 2 points, it's the same score, then I wouldn't have this confusion that I just described. But this is close. This is a good idea. Does the subtlety make sense? Okay, I hand waved a lot. Okay. All right. So if you keep working at this, you do eventually come up with something. It's a bit tricky. Okay. So this is. I'm not saying this is easy to come up with, but at least somebody once came up with it, and we can just look it up on the internet now. Okay. So we're going to introduce a new variable y. Okay? And I'm going to make these 10 clauses. One is this, I have 3 singleton clauses of A and B and C. Then I have these all like pairs of negations. Not A or not B, not B or not C, and not C or not A. That's all the pairs. Then I have 4 more clauses involving y. One was just y. One was A or not y. One was B or not y. And one was C or not y. Okay? I wish I had a better explanation for how to come up with this even in hindsight. In fact, I simplified this a little bit from what I found, but still, I don't have a great explanation. But we can verify that it works. Okay, so we're just going to check and see what happens. And basically, up to symmetry, the 4 basic cases. One is that they're all false. All A, B, and C are false, and the whole thing comes out to false. How many points can we get? 2, one of them is true. Since it's symmetric, I can assume A is true, but it would have been the same if B was true or if C was true. The next case is if 2 of them are true, and I'm assuming just A and B are true. And the third case is when A, B, and C are all true. So what I want is the total for the last 3 columns to be the same and bigger, or at least different, than the total for the first column. Okay, so I split it up by rows because actually I wasn't able to add them all up at once. I had to group them to see. Okay, so we're just going to knock out all of these boxes. So do the boxes make sense? So let's take the top left. If I had false, 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 how many of those first 3 clauses am I satisfying? 0. Good. And now going down to the second row, false, false, false. How many of those pairs of negations am I satisfying? I heard 0 or 3. So the falses become true. Okay. Now the goal is to maximize the number of clauses. So if I had false, 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 and I wanted to choose y to maximize the number of those remaining clauses involving y to satisfy, what's the best I can do? 3. So I would want to set y to be false. The total score is 6. All right, only 3 more columns. All right, First row, second column, true, false, false. How many? 1. All right. Second row, second column. How many do we get? That's right. Someone said 2, but I think it's 3 because 2 of them are false. So any pair should. 2 out of 3 are false, so any pair should get one of the negations. Okay. And then lastly, if I have true, false, false, what do I want to set y to be? What's the most points I can get? Sorry? 2. You can get 2 points if you set y to be true. How many points you get if you set y to be false? I feel like today you've had bad luck. You just flip whatever you're going to say. Okay. All right. So you get 7. All right. All right. 2 more columns to go. All right. First row, third column. I have true, true, false. How many of those clauses do I get? And then now, how many of these pairs do I get? 2, because it's only the 2 pairs involving that one false. And then finally, for the last row, what's the best choice of y? How many do I get? Yeah, actually, does it matter? I think either way you get 2 points. Okay. So you get 7. Okay, good. So at least the first 2 match. Okay. Last one. True, true, true. How many do I get from the first row? How many from the second? 0. And how many from the last? 4. Because we set y to be true. So we get 7. Okay, so here is sort of a gadget. It's a little complicated. I'm not saying it's easy to come up with. You'd have to, think for a little while to come up with this. But what it does is, if that clause was originally unsatisfied, then you can only get 6 points. But if the original clause was satisfied, then you get 7. Okay? So you get this 1 point gap, and it's consistent. It's always 7. Okay. So, yeah, okay, this is just stating it in long words. All right, so, okay, so we can apply, so that lemma just describes what we just did. Okay, so I'm going to take each of these 3 variable clauses, turn into 10 clauses, just like we described, and introduce one more variable. And in that sense, I can go from a 3-sat formula to a 2-sat formula. Okay, I put it in the black box. Okay, so, and it gives me some maximum number of sats. It tells me what the maximum number. Okay, so let's go through this a little bit slowly. Let's say that the original 3-sat formula has m clauses. How many clauses does my auxiliary formula have? 10m. So maybe you guys lost count, but there was 10 auxiliary clauses that was created. So if everything's satisfied, you get 7. If at least one of them is, if it's unsatisfied, you can only get 6, right? So, okay, so this black box outputs some number between 0 and 10m. And I need to turn this into a yes/no for the original question. How would I do that? Seven m, 7m out of 10m total, right? So 7m means that I satisfied 7 out. I can only satisfy as most 7 from each family, and I can only satisfy 7 if x1, x2, x3 satisfied the original thing. So if I'm able to get 7m, then I'm getting 7 out of each of those gadgets, and that means I'm satisfying each of the clauses corresponding to each gadget. So I'm satisfying each clause in F. And if I get less than 7m, right, I can get at most 7 from each one. So that means there's some clause where you can't get 7, right? Actually, we should do this a little bit more slowly. Let me go backwards. Suppose F is unsatisfied. Let's do this slowly. All right. So if F is not satisfiable, okay, so you have to do it back and forth. So to do this correctly, say, oh, if F is satisfiable, right? I need to do this quickly. Let x1 through xn satisfy F, right? And then given those, choose y so that you satisfy, choose each of those yi so that you satisfy 7 of those 10, and then you'll get 7m satisfied clauses in the original one. Conversely, I want to show if f is not satisfiable, then no matter what, there's less than 7m that are satisfied in G. Okay? So let x1 to xn be any thing. Actually, we have the x1 through x1 and we have the y's, right? So for any choice of x's and y's, I want to show that I'm satisfying less than 7m, right? But f doesn't satisfy, f is not satisfiable, right? So there's some clause where the x's doesn't satisfy that clause of 3. And in that clause of 3, you can only get 6 points. So you must get less than 7m overall. Okay? So that'll get you both directions. I'm only not writing it for sake of time. If f is satisfiable, then you can choose the y so that you get 7m total. If f is not satisfiable, then for any choice of x and y's, it has to be less than 7m. Because in particular, whatever clause is not satisfied in f, you can only get 6 points. Okay, so I would write that in full if I had a little more time. Okay. All right, so in the remaining time, okay, so that establishes that max less than equal 2 sat is tough. Now we just need to go from less than equal 2 sat to 2 sat. Right, so that's a smaller leap, I think. All right, I think you'll be able to guess this. Okay, so I want to show that polynomial time algorithm for max 2 sat implies a polynomial time algorithm for sat. That was the original claim. But now, instead of having to go directly from like 3 sat, I can go from less than equal 2 sat, which is even closer to 2 sat than 3 sat is. So I can start with an instance of less than equal 2 sat. That's not a great picture because, for various reasons. Okay, it's not a great picture because this should only have 2. And also, this should not be less than equal to. Okay, so you have a black box for 2 sat. And you're given an instance of less than equal 2 sat. And you want to turn your less than equal 2 into some instance of 2 sat, plug it into your black box for max 2 sat, out comes a number, and then convert that number back into something related to less than equal 2 sat. Okay. All right. So here's the basic question. I want to give you guys a chance to guess. So you're given as input, some formula that, every clause has 1 or 2 variables, right? So the one variable clause I call singleton. So it has, let's say, k singleton clauses and L 2 variable clauses. At some level, I just need to turn my singleton clauses into 2 variable clauses. That's the only real issue. Okay. Any ideas? Let's say I have a clause like A. How can I turn this into a 2 variable clause? Yeah. Oh, like this? Oh, that's cheating. Okay. It's got to have 2 distinct variables in each clause. Okay. So no topological. Oh, wait. Okay. So if you did this, if I replaced every A with A or A naught, that actually wouldn't help you because previously you wanted to choose A. Now you get a point if you choose A naught. What? Okay. So you start with A. Okay. Anyway, just avoid reusing A for this because it's cheating or won't work. Okay. Okay, we can make a new variable Y and write A or Y. Okay. That has 2 variables. But I could just set Y to be true and on Mac would get the point even if A was false, right? Sorry? And A or not Y. Okay. This way, I have it all set up. Okay, that's exactly what I wrote. Okay, good guess on Y. All right, so why is this nice? If A is true, right, no matter what I choose Y to be, you're going to get 2 points. So 1 point turns into 2 points no matter what. And what if A is false? 2? 0? Try one more guess. You always get 1 point. Whichever one, if Y was true, you get 1 point. If Y is false, you get 1 point. So you're always getting one more point than you would have gotten from just A. This is actually much easier than last time. We have to go through a whole table to verify it works. Okay, so now it's pretty straightforward. I'm going to make a formula where I take each of these singleton clauses with some literal AI, make a new variable yi, and do ai or yi and ai or not yi. Okay. All right. So, and then the proof is more straightforward too. If x1 through xn satisfies p clauses in f, right? Then for any choice of y's, how many clauses do I satisfy in G? The last question. If I satisfy P clauses in F, and G is made by replacing the singletons with, it's not 2P, because not just doubling. Well, because there's singleton clauses and there's two variable clauses. There's K singletons and L two variable clauses. Yeah. 11 over 14M? There's, no, this is just a general, F already has K singleton clauses. Yeah, I'm already giving you something in less than equal to set form. So it's not 3 set anymore. So now we already have less than equal to. So there's K singleton clauses. Let's say there's 100 singleton clauses. Sorry? P plus K. Right? Because each of those singletons, we basically get a free point. 0 goes to 1, 1 goes to 2. Okay. All right, good. So the maximum number of satisfied clauses in our auxiliary, our new one, G, is always equal to the maximum satisfied in F plus K. Okay, I'm just getting K free points from the singletons, the K singletons. Okay. So that completes our thing. We get rid of all the singletons by just adding yi and yi not. And then we go through, and whatever the answer is, you don't add K, you subtract K from what the black box tells you, and you get the maximum number of satisfied clauses in F. Okay. All right, then that is finally it. All right, see you guys Thursday.